In the past, we've discussed structures like this small tetrahedral object, which is a triangular neighborhood structure, and then through a series of demonstrations, we rose at one point or another to the icosahedron. In this part of the video, I'd like to explain to you how one goes about constructing such triangular neighborhood structures in the computer, which is quite different from how structures like this might develop in natural triangular neighborhood systems. So let me start with the smallest structure, the tetrahedron. So it's clear by observation that this has 4 three-edged nodes. And so we start with one node here called 1. And we then have a grammar that says there are only three-edged nodes, and every node has 3 neighbors, and each of those neighbors are three-edged nodes. So we look for a rule, and the only rule that's here is this one here. So we apply that to this central node. We say that it's a three-edged node, because that's the only thing it can be. And then there are 3 nodes that are out from it. So this is node 2, this is node 3, and this is node 4. And of course, by doing that, we will also say, in clockwise fashion, this is a three-edged node, this here is a three-edged node, and this one here is a three-edged node. So now we go to node 2 and say, well, what rule can we use? There's only one rule. It fits three-edged nodes. There could be other rules in a more complex grammar. We then say, well, are any of the nodes, how are the nodes specified? And in this fashion here, we can say, well, the node 3 is specified as a three-edged node, and node 1 is specified as a three-edged node, and node 4 is specified as a three-edged node. So we can draw connections here like this. And then we the program goes now to node 3, looks to find a rule. It says there's only one rule that fits its description as being a three-edged node, and in a clockwise fashion, the 3 neighbors have to be also three-edged nodes, and that's in fact true because node 2 is a three-edged node, node 4 is a three-edged node, and node 1 is a three-edged node. So you can apply this rule, which results in the formation of this. So now we go to, the program will go to node 4 and looks to see what rule it could apply. There's only one rule for three-edged nodes, and in the clockwise fashion, node 2, node 1, and node 3 are each three-edged nodes, and so it applies the rule. But of course, all the connections are there already, so then the program simply exits. So this is the development of a simple tetrahedral structure like this, a grammar for constructing, and then the process of constructing. So the next structure we want to study the grammar for is the icosahedron. In the icosahedron, there are 5 edge nodes, and all 12 of the nodes in the structure are 5-edge. So we can write the grammar for this structure very simply. It's a 5-edge node, and then each 5-edge node has 5 edges around it. So we can start with one node, as we did with the tetrahedron, put in 5 neighbors, and then we can begin to apply the program to the other nodes. So the second node here will then generate this as well as this, and the third node will generate this node, this connection here, as well as this connection, and so forth. So the program will go from this node, the first node, around to the back, where there'll be all of the 5 edges already in place, at which point the program will end. The next structure and final structure to be shown for the grammar for is this flat structure. Here I've colored the 6-edge node in orange, and we start out by saying, oh, and then we notice that there are 12 5-edge nodes. Each 5-edge node has one 6-edge node and then 4 5-edge nodes around it. So we can write the grammar as 6, 5, 5, 5, 5, 5, 5, and then 5, 6, 5, 5, 5, 5. And so the program will go to the first rule here, lay out a 6-edge node like this, and then go to the second node, which will then put in these connections as well as putting in these two connections. Then it'll go to the third node, fill in this connection here as well as these two connections here, and then proceed all the way to the end of the structure. Once again, we start at this point and it goes around and eventually fills in these nodes, and then finally the 6-edge node at the far side of the structure is processed, and at that point all of the connections to it are already available, and then the program will exit. In the past videos we've seen structures different sizes with different numbers of edges coming together at a node. And I might have mentioned on occasion the notion of curvature, but let me just present this slide here. This is a table showing the node size 3, 4, 5 to 9 and the curvature. So the easiest way to understand this, of course, is that the 6-edge node is flat and there's no problem about curvature, whereas a 3-edge node is very curved, and the 5-edge node is less curved. This table in general goes from the negative curvatures through the neutral curvature to the positive curvatures. So I just realized that I can use the Knupfli rapid prototyping tool to illustrate the idea of curvature much better than just the table. Here's a 3-edge node where the 3-edge node is in light blue, and then I've used the pink to close off each of the triangular neighborhoods. So this structure is quite curved. If I bring a 4-edge node here and show you that it has the concave structure just like the 3-edge node had concave structure. Then by comparison, the 4-edge node is less curved. And the 5-edge node is even less curved. So I'll just shift these over a bit. And then, of course, the 6-edge node is flat. So these are the negative curvature nodes. This is the neutral. The 6 is the neutral curvature node. And here's the 7-edge node. So the concept of positive curvature is a bit more difficult to understand. I mean, certainly with the negative curvature, you can see the concavity as the principal feature of the node construction. But the 7-edge node has a positive curvature. It's one could say a weak positive curvature. And we'll talk about this in some extent later on. Here's an 8-edge node, and it has much greater positive curvature. So you can see how the Knupfli edges, which are unit length and half the length in width, work very nicely to show how, if you have uniform triangles that are each unit length long, that the effect of having 8 such edges put together in this loose weave works to produce the curvature. And then, of course, here's the 9-edge node. And you can see it has extreme curvature. And yet it's perfectly balanced and changeable and fluid. And there's a whole nother video at the end that discusses the curvature in terms of the stabilization of these conformations. So here we have the 7 models, 3, 4, 5, which are negative curvature, 6, which is neutral, 7, which is a weak positive curvature, 8, which is a stronger positive curvature, and 9, which is even stronger. Now, in principle, one could have 10, 11, 12, whatever curvatures. I just never built those. I'll have to really think about using this particular scheme of representing curvature and start building models, these primitive models, with curvatures of 10, 11, 12, which I've just never done that before. Isn't that amazing how you find these things? If you have a relatively small structure that you're constructing and it has 12 5-edge nodes in it, and these nodes are in some way close to each other, you can construct a grammar that will, starting at a given node, will be able to construct across to the other curved nodes, like this, and then like that, and eventually you'll come around to the far side and the structure will close. But if you're one of the things I discovered was that if you're constructing large structures like this, and they're only the 12 5-edge nodes, and some other 5-edge node in the model, the structure over here, some distance, you can't, and there's all 6-edge nodes in the middle here, you can't, the grammar can't get across all of these things, because at some point it'll just be all 6-edge nodes here, and that's just the C. I mean, we see this in the case here of the ground state. I mean, there's huge amounts of, so the distance between here and here, there's nothing specific about how to construct these nodes between these two places, and if you want them to be exactly that number. So one of the things that I've realized is that you have to have a model in some cases, and the model can say, well, we start here, and the model will tell us how to get across to here, and of course then be able to get around back to here. So that's what this loop-like notion is here. And so for the torus zeros, a model like this is sometimes necessary, but in the smaller structures there's no need for a model like that. Now we can begin to introduce the notion of toruses. And here's a torus of a particular construction, shown in green and with the extra trace in it of yellow. So the characteristic of the torus zeros is that somewhere, no matter how big they are, somewhere in the structure there'll be 12 5-edge nodes. And that gives you a total negative curvature of 12 times minus 1, which is minus 12. But the characteristic of a torus, a donut in this case, is that you have the 12 5-edge nodes throughout the structure, but you also then have 12 in this case 7-edge nodes. Yeah, and so there are 6 here and 6 here. But one of the things in developing the grammars now, 50 years ago, I realized that you couldn't construct a torus with a single level model. What would happen is you'd start off at some spot, and it would build outwards, and then it would build around this way like this. But because when the grama got over here, it would continue to build like this. And in the same way, if it started here, it would build out this way, but then it would continue to build itself around like that, and it would never terminate. And there was no set of rules that I could discover for myself that would eliminate this problem. So the result that I came up with was that one had to build a two-level model. The one ring of structure specifies the closure of the hole of the thing, of the torus, and then the other ring specifies the outer portion here. And so in this particular model, I've done this in yellow. And so you see the one ring here, which corresponds to this ring, and then the other ring here, which is specified by this pink thing in this little model. So whenever you want to build a torus, you have to use a two-level model. And I found that really rather interesting. You need a metagramma for the structure. So I showed you this green torus here. It has a particular construction pattern. And so here's another structure that's somewhat smaller, done in yellow with the meta model shown in green at this point. And this structure has the same ring-like portion, but this is much smaller. And somehow this structure here, for example, and here, this structure has edges that are bent. And as I said before, whenever you see something like this where the edges of the plastic knupfli elements bend, you come to suspect that there's something wrong, so that somehow this yellow structure is smaller than it should be. And it's a very curious notion, but there it is. But in addition, this is the same organization of the nodes in the center here, but instead of completing it as we did with the yellow and green models, this is how the toroidal hole would look just in the middle of a ground state, two ground states. So there's one ground state that runs this way, and then on the other side it's skewed to that. You see the way the thing, well, I said this way, but let's think of it this way here, and then this one is this way. So this would correspond, for example, if you had a pinching in space-time where a toroidal hole would be the connector. The orientations of the ground state have to be different in that case, which is rather interesting. So here's a case of a toroidal hole, a three-hole, embedded in the middle of a pipe. And this is about as small a construction of a toroidal hole embedded in a pipe as I can configure. So in the same way that ground state was scaled, we can also scale toroidal holes. So this is the same hole topology. This is a 7-edge node here, and another 7, and another 7. So there are 6 7s around in a row. Here, there's one node between each 7. These are the 2 7s. See whether you can see that. 2 7s, yeah. And so this is a larger hole. And so the holes scale rather nicely. The same comment can be made about this type of hole. This is the up and down hole. The 7-edge node is here, and then down, and then up, and then down, and then up. This is acutely skewed to each other. That comes across rather well. We can scale this node here. Once again, you see the 7-edge node, 7 down, up, down, up, down, up. So these scalings are interesting. How the structure of the toroidal hole changes quite dramatically. So the real question in the scaling is when we try to move the toroidal hole. I've not succeeded in doing that yet, but there's some sense that the curved nodes, the 7-edge nodes, have to be separated from each other. Now, whether a separation of just one node is enough or not, or whether it have to be scaled more, that's still not clear. But the effect of this type of hole, when it's built per se, is that it forms a rather elegant triangular object, which is just interesting, you know. So I bring back the green torus that we've seen before, only now I've added blue edges just to mark where the 5-edge nodes are. So you see this is a 5-edge node. So when you look at this structure, there are 6 on the top, and then if I turn it upside down, there are 6 5s on the bottom. And this structure looks symmetric, or it is symmetric, and looks at rest. But here are weird objects. This is a twisted sort of torus. You can see what it looks like. Only this has 14 5-edge nodes to it. And part of the reason is that this hole here is no longer 6, but it has 7 nodes in it. And this forces the twisting of the torus. This is not the only state. I found another one here. This also has 14 edges, and if you look at the holes, you can see that the one on the pink one on top is a bigger hole in some sense than the one on the bottom. So the purpose of these this part of the demonstration is to show that the symmetric structures have a rather regular thing and have an edge, have 12 5-edge nodes around the outside. But because there's more curvature here in the hole here, then you have to have more curvature on the outside of the torus. And the same is true for this one here. So that's, you know, these are all just interesting properties. I don't know what to say about them any more than that. So I don't know how well this is going to come across. But this is a toroidal hole. And unlike the ones that are symmetric and up and down, there's 2 ground states here, you can see, but the structure, the hole itself, is tilted and twisted. I've colored the bottom half green, the junction between the 2 halves in yellow, and then the upper half in red. The ground state in this case is in blue. So that's one structure state that I found. So this is a similar structure. Again, the coloring is the same. The green is the bottom half, yellow is the boundary, red is the upper half, blue is the ground state. But this is a larger state than the previous structure. and one has the sense that the structure is, the hole is moving in this direction, for example, whereas any of the other holes that we've looked at are symmetric and would seem to be at rest. Well, we've seen the icosahedral and the flat structures. In the same way, we can take any of these structures and, as I showed before, merge them onto the ground state plane. So I've done this with two sample structures. Once again, the icosahedron and the flat structure. They're bonded directly, in this case, to the ground state plane using 9-edge nodes. And this is a perfectly good example of taking a torus 0 and bonding it to the ground state. Well, in the same way, we can take a ground state and bond a toroidal object to the ground state. So now I've taken the green toroidal object and the ground state and concatenated them together. You can see in this instance that the interfacing structure is a 6 circumference pipe rather than a 3 circumference pipe that I've been using in the past. Now the interface with the ground state is a 6 pipe here, quite big, and as the green toroidal structure had no 6-edge nodes on the surface here, I chose a node here to act as the interface to the 6 pipe. And so now you can see how the structure is constructed. This 7-edge node here, with the addition of 2 of the pipe edges, becomes a 9-edge node. And over in the corner here, the 5-edge node that formed the corner of the turning surface of the toroidal object becomes a 6, and then these are 7s and so forth. So this is the toroidal object is now, in a certain sense, at a crazy angle to the ground state. If we took the toroidal object and scaled it up by 1, well, then there'd be plenty of 6-edge nodes on the periphery of the structure, and then we could have it in a vertical position like this. But a 6-edge pipe could be anything. It could not anything. It could be a 12 circumference pipe if we scaled up things appropriately. But this just shows that any toroidal object can be interfaced by the ground state, whether we use a 3-edge interface or a 6-edge interface. It's just a question of scaling more than anything. But it shows that the toruses come in a variety of sizes, and then the interface can be in the pipe, in this case, can be of various sizes, and the interface with the ground state has the consequent size. The point of all of this is that there are just a huge number of different, if I say energy states, I hope you won't be offended, but different structure states of different levels of complexity and scaling and interrelationship. So now I'll show you a bunch of other toroidal objects in no particular order. So here's another toroidal object sitting on a short pipe attached to the ground state. The object is in the light blue, the ground state is in green, and the interface pipe is in purple. This is a relatively small structure, relatively unsymmetric, because the hole is a 3 hole, and this resulting structure is a consequence of the structuring of the three-hole itself. Here's another variant of that same structure, again a three-hole with a bit more structure here, and now interfaced in a vertical fashion to the ground state. Of course, as we've seen before, there can be long pipes attaching the toroidal object to the ground state, and as we just showed, needn't have a three pipe as the interface. So here's another small object, even more distorted, asymmetric, attached to the ground state. And then finally, here's a relatively symmetric toroidal object attached to the ground state, and shows just how the toroidal object can, in this case, be upright, because it has a 6-edge node on the periphery of the structure, and so we can use or 3-edge nodes. We can use that, or we could use a 6-edge node here as an interface. So these are just different ways in which tori, torus ones, in this case, are connected to the ground state. So let's go from single-holed toruses or single toroidal holes. Here's a construction of 3 circumference toroidal holes right adjacent to each other. You notice that they're slightly tilted into each other. So the structure is sort of bowed in this fashion here. But these are these are 8-edge nodes. So each of the 3 on the top and 3 on the bottom, each 8-edge node has a curvature of plus 2. So that's a plus 12, 6 times 2. So this same structure can be completed, and it looks like this now, with the toroidal holes here and the ground state, in this case in yellow. So in a certain sense, any of the objects that we've looked at before can be mounted on a 3-pipe, as we've seen a ball mounted on a 3-pipe before. We can take any of the toroidal objects that we've looked at and bind them to the ground state, whether they're two holed toruses, as we've just seen. Here's a torus that is also bound to the yellow-green ground state. This has 3 entrances, and that's characteristic of a torus 2. So there's always one more entrance or exit than the toroidal number. But here's a case where there are 3 holes in the entrances to the object. And again, this is a somewhat unsymmetric structure. And that's 3 holes. Here's a bit larger structure with 4 entrances and exits. So this is a torus 3. And again, it's bound to the ground state, in this case in yellow. And this is a mostly symmetric structure, not quite. I guess it is tetrahedral in the center. So this is a symmetric structure. And as always, any of these structures can be scaled up by putting nodes in between. Here's talking about single holes. This is a curious object. It has a 5 circumference here on this side and a 6 circumference on that side. So the hole changes size as it goes from one side to the other. And then you need all of this compensating structure around here to complete the structure. Again, you know, I don't know what these things mean, and one could question, well, why am I showing them if I don't know what they mean? It's more that I have an idea about a construction. For example, in this case, I asked myself the question, could a toroidal hole have one diameter on one side and another diameter on the other side? And so that's just an idea. And I then spent some time, perhaps half a day or so, playing with the construction of the hole itself, and then building outwards, again what appears to be, for this, a minimum structure. That is, there was no way of having a 5 here and a 6 here and having anything less in the way of structure here. So this is just an experiment that I made, and I can't attribute a meaning to it, and yet one could argue it must have meaning in some way. Here's another weird object where there are 1, 2, 3, 4, 5 toroidal holes, but inside in red, it should be done in a different color, there's an inner structure in there. So this is a torus 4, but with an inner structure, and I don't know what these things mean. This thing could be colored a bit better than it is. So in editing the previous section of this video, which was concerned with a question of a hole, a toroidal hole that was 5 in circumference on one side and 6 on the other side, I said to myself, well, could I do this for other situations? And so I started out with a 3-hole shown here, and this 3-hole is triangle-centered ground state in green. And then I added what in the end were 3 7-edge nodes to the beginning of a pipe. And then I built it out as 3 more 7-edge nodes here, and then filled in the ground state. And lo and behold, this is a hexagonal, a point-centered ground state. So the effect of this toroidal hole is to convert a triangle-centered ground state into a node-centered ground state. And that's, I mean, it's probably in the end just one of several such conversions, but that's fantastic, because now I understand, I think, I could start out with a triangle-centered ground state and convert it to a 4-field or a 3-field or a 5-field. And there's a whole other video that deals with fields and stabilizing particles. But now I see the generalization of the process of converting one ground state into another. And so this is, you know, a tremendous reward for doing this. I see something now that I've never seen before. That's amazing. So this is a construct that includes larger scale icosahedron and then 3 single hole toruses. I can bring this up closer, and we can see the structure of the torus rather nicely. I can bring it around here like that, and you can see the purple edges are the 7-edge nodes. that form the torus, and then also the 7-edge nodes that connect, 8-edge nodes, connect the pipe to the icosahedron. So there are 3 instances of the structure. This took me, about 2 or 3 days to construct the torus using that meta model. And then Dan Rowe, who's in the Heart Institute of the NIH, did some work, helped me he wrote a script for using amber to minimize the distances to make each of the edges be as close to unity as possible. And in doing so, it was possible to spatialize the torus and as well the icosahedron. So the process is first constructing the icosahedron, then constructing the connectivity for the torus, concatenating the torus through a pipe, and then that construct to the icosahedron, and then running it through the amber minimization script that then puts it out in free space. So this is, for me, great progress, because I'd never been able to do the construction of the toruses myself in free space. The other structures that I've shown, the pipes and the icosahedra itself, and I could do that from mathematical principles, but the torus needs something more than that. And so the amber script that Dan Rowe wrote for me did this rather nicely. And so later on we'll see the icosahedron deforming, and that's certainly very exciting.